Okay, so for those of you who don't know me, that's me. I'm Mike Meadows. I'm a consultant at Insight Digital Innovation. Insight is we used to be Cardinal Solutions and Blue Metal, but we joined together and we do lots of cool stuff. I currently do a lot of things in the cloud. This talk is kind of based on some of that because what I deal with specifically are distributed systems. The information up here, I'm going to point up there, but I'm going to point down here too, is how you can get a hold of me. The slides and any material related to this is going to be at that shortened link there, Meadows/ST19. And sorry, I'm going to do this because I'm used to doing this. Excuse me, people in the other room. I'm used to doing this. And so I'm going to get all fidgety because I have this little white box that I can stand in. Hi, guys, again. My GitHub and my email. So any of those ways you can get a hold of me. I'm really bad at Twitter, so that's probably the worst way to get a hold of me. So this talk, everything you always wanted to know about distributed applications but were afraid to ask is actually based on the title of a movie by Woody Allen, which was loosely based on a book by David Rubin. And this movie was released in 1972, but I can tell you as a teenager, I was fascinated by the title. I wanted to know everything about this movie. Now, I didn't get to watch it until years later. I think I was in my 20s, and I went to a Blockbuster, and I picked up like 4 different Woody Allen movies so that the only one that I was getting wouldn't be everything you always wanted to know about sex. It was disappointing, but what I had I don't know, like 10 years worth of expectations built into it, and it wasn't really what I thought it was going to be. But what I did like about it was that it tried at least to answer the questions using allegory, right? So it didn't actually answer the questions. It was really just a run-of-the-mill Woody Allen movie. But it didn't go at the question directly, right? So this talk, I did a very similar, am I shiny? Sorry. I did a very similar talk to this. It's at CodeMash in 2015, but it looked a lot like this. So, I'd had good attendance, I had good feedback, but I can't imagine that if I were watching this, I wouldn't be asleep. So I wanted to figure out how to tell this story, how to prepare you guys really to understand the underlying theories and technologies and all of that goes into distributed systems without having to explain why W cannot be less than n plus 1 divided by 2. If you guys want to know that, feel free to ask that as a question. I can explain it. So this story is going to be told in 5 acts. And the first of those acts is, what is so complicated about distributed systems? So, and it's always a losing battle, but I'm going to try to get participation at 8:30 in the morning. How many of you work in truly distributed systems or systems that have a lot of distribution? Hey, how's it going, man? A lot of distribution. Okay, so what is complicated about it is really boils down to 3 things that we can put together in CAP theorem: consistency, availability, and partition tolerance. Don't read the words. I'm going to show you the words later. But CAP theory is one of those magical triangles where you communicate, you at least try to attempt to communicate. Why does this thing, it thinks I've been presenting for 24 minutes. Hey, where's Arn Alpha? Okay, I'll catch him later. Try to communicate that there are a trade-off that you have to make between at least one of these 3 things. So if you want consistency and you want partition tolerance, then you must give up some of availability. Now, it's not an all or nothing. It's not a zero-sum game. There are techniques that I'm not really going to explore here where you can gain in 2 and not give up as much of the other. But to keep it simple, we're going to say if you want 2 of these, you're going to have to give up the other one. So, to tell this as metaphor, as a story, rather than diving into the formulas and all that stuff, I'm going to tell you a story about the world's largest retailer. Delivers almost anything you want to your door. It offers a lot of services, and it is an internet pioneer. And if you guys think you know the answer to this, you would be right. It's Sears in 1981. In 1981, Sears was the largest company in this space at 1% of US GDP. So contrast that to Amazon, who we think sort of rules the world today at 0.8% of GDP, right? It was actually, believe it or not, an internet pioneer with Prodigy. So they partnered with IBM on Prodigy, which brought the internet to a lot of people. And more importantly, what we're going to explore in this act is its catalog service. So with the catalog service that Sears had, it was so successful that it actually forced the US Postal Service to change how it did business and actually deliver out to rural areas. It brought penetration into parts of the country that were not served in previously by the Postal Service, very similar to what Amazon is doing now. So if I'm in charge of scaling this catalog service with Sears, I'm going to be faced with that same sort of trade-off with CAP theorem. So we're going to try to explain that in non-technical ways as much as possible. And in some places that breaks down because I really do have to dive into the technical implications. But the definition, at least according to Wikipedia, is for consistency, every read receives the most recent write or an error. What this means is that you can always build your systems with the expectation that if you put something in, as soon as that's done, you and everybody else sees that thing. It's always consistent in that way. It's a little bit different than consistency when we talk about atomic consistency, but it is close enough that we can sort of think of them as the same thing. Now, from the perspective of Sears and their catalog service, what this means is that I have to make sure that if you put an order in, that doesn't cause an issue with anybody else's order, and that if you ask me a question about that order, you're always going to get the most current and correct answer. Well, as the executive in charge of this, what that means is I have one really big fulfillment center, like really, really big fulfillment center, probably in the center of the country, right? In addition, I only have one team that's allowed to actually deal with the paperwork of fulfilling these orders. In a purely consistent environment, I can't afford to have two teams or more doing the actual order fulfillment because there will be an issue with them communicating with each other. In a perfect scenario, there's only one person doing it, right? So you can kind of see why consistency is the enemy of scale in this case. In addition, I also have to make sure that the inventory is segregated or isolated in such a way that when I start fulfilling an order, if I hit a room that has a particular piece of inventory that I need to put into an order, I lock the doors. Nobody else takes anything out of that room until I finish fulfilling this order, at which point I can unlock it. Now, if this sounds familiar to you, and again, see, I say I'm going to tell it in allegory, but I really have to jump back to the technology. These are the types of things that we hear when we talk about relational databases, right? We talk about isolation, locks, consistency. It's really great, but the problem is there's difficulty in scaling it, and I'll sort of explore the combinations here after I talk about the first three. The second one is availability. So, does anybody get this joke here, by the way? No? Okay. The Waffle House index is actually a real index that's used to measure how bad an emergency is, because apparently it's got to be really bad if the Waffle House is closed. So to guarantee availability, I have to be sure that catalog orders will never be lost. If you submit an order, I will either immediately tell you, hey, this isn't going to work, or it will be there, right? I might not be able to fulfill it immediately, but I will have it, right? If you're going to call to find out what's going on, you will always be able to get a hold of somebody. You're not going to get a busy signal, and you're not going to get disconnected, right? But more importantly, most importantly, I would say, is that you always get an answer, right? And that answer may be incorrect, because now we're not necessarily guaranteeing consistency, but you will get an answer. The final one, partition tolerance. Here, that can get distracting, right? So partition tolerance, and there's a lot of words here, but basically what it means is that if the Black Knight loses all of his limbs, it's okay, because eventually you will have a fully functional Black Knight again. In terms of Sears, what that would mean is if they chose to go with a distributed fulfillment organization, they would have many fulfillment centers, and if any one of those fulfillment centers, or even 10, or even 99% of the fulfillment centers were unoperational for a period of time, it would be okay, because the system itself, the system of fulfillment, doesn't go away, it just becomes unavailable. So, and that bullet is really my way of apologizing for the bullet points here. But it's kind of, they're kind of necessary here. So when we talk about, so what does it look like if we have a system that is consistent and available at the cost of partitioning, or partition tolerance, sorry. For Sears, what that means is that they have one warehouse and only one warehouse that's allowed to fulfill orders, perform accounting, basically all of those things that are what we think of in terms of fulfillment, right? They may have other warehouses, and those other warehouses may also have inventory, but they're not allowed to fulfill orders. They're there kind of as a backup, right? They may also provide inventory. They may also help with replenishment of the primary warehouse, but in general, you want them to have the same things, because if for any reason they're unable to fulfill an order from the primary, one of the secondaries immediately and transparently takes over as the new primary fulfillment center. Now, if we throw away availability, but we keep consistency, and we want consistency and partition tolerance, and we got more bullets, so I continue to apologize. I think these 3 slides here are the ones with all the bullets. We'd still have a giant primary warehouse, but we may have other secondary warehouses that might not be as big, might not have as much stuff in it, right? We don't have to keep them fully stocked. All we have to do is make sure that if the primary goes down, that we are able to bring one of the secondaries up to replace it, at least for a temporary period of time, such that we can continue to fulfill orders, and then eventually we can switch back to the primary, right? So in this case, availability isn't what we're shooting for. It's really just to make sure that the system can survive. And then the third one, which is really where we usually end up in distributed systems, is, there we go, there's that, sorry, I was saying that I fidget, so I'm eventually going to end up like breathing into the mic or knocking it or something. Availability and partition tolerance with a trade-off on consistency. So what this means is that we have multiple smaller warehouses spread throughout the country, each one able to fulfill orders, right? That is what we call multi-master. Each warehouse is really targeted to its local area, and that's what we call partitioning. But in addition, when you place an order, we send a copy of that order to at least a couple other warehouses. That's called replication, right? So that if the primary smaller warehouse that you're trying to place your order in isn't able to fulfill that for whatever reason, it catches on fire, or everybody goes on strike, we're able to fail over to one of those other warehouses. And then finally, in order to make sure that those orders are being fulfilled properly, all of the replicas of that primary warehouse need to agree on the order before it's fulfilled, and that is called a quorum. So I know it's probably still really heavy, and we're about to start the next chapter. want to give you guys a chance to ask me questions now before you sort of lose it in our next segment. Are there any questions? Okay. And I'm not watching the Slack channel, so we're good? Okay. So the next question, the second act, is how do I build systems if my transactions aren't ACID? So this is a question I get a lot as I try to help organizations sort of modernize their applications, right? When we explain the reality of being in the cloud and that you have to trade off consistency. This question comes up a lot. So in case you're like, why does that say Fight Club? The joke here is base. So if you haven't seen Fight Club, I'm going to give away a part of it. They go to a liposuction clinic and steal a bunch of human fat and then mix it with the base and turn it into soap. So again, don't read the words, and in fact, really don't read these words because this base acronym is really silly and doesn't really work. I fully suspect that it was a backronym. So what I'm going to do is I'm going to take these terms and put them in my own words and probably completely butcher them. But as I see it, it's a trade-off in this case between, or it's not a trade-off, but it's an understanding the relationship between the responsibility of the data, the responsibility of the process, and the responsibility of the application. So, by the way, I don't know if my clock is all messed up because I started the presentation like a long time before I actually started talking, so I have no idea where I'm at on the talk. Okay, so this act is told from the perspective of people living in the belt in The Expanse. Anybody a fan of The Expanse? Okay, I love this show. I love the book. Basically, the premise is, and this is Bobby Draper, by the way, who is the coolest character at least in the TV show. I haven't gotten to the part in the book where she comes in. Basically, Earth is expanded out into the entirety of the solar system, and there are three factions: Earth, Mars, and the Belt. And in the book, it explicitly says that the Belt is a distributed system, right? None of the stations in the Belt are big enough for one station to be completely self-sufficient. They need each other, right? But there's a limitation here, which is that in the case of living in the Belt, the speed of light actually becomes a limiting factor in communicating. So I thought that would be a great way to talk about our topic, base, which is how to live in a world where you can't have consistency, where it's just not possible, right? Okay, so basically available, which is the first part of the base acronym. From my perspective, what this really means is that we have to understand the responsibility in terms of data, right? So how would a space library be able to fulfill the request for information? And when I say space library, I actually mean a real library on a space station. So we have to assume that the library, like most libraries, don't have everything, all in one place, right? They're not the Library of Congress. So, if I were on Series Station and I went to a library and I'm like, hey, give me this obscure book, how that station will fulfill that, how that space library would fulfill that is simply to say, okay, I have that book, here you go, or I don't have that book and I don't know if I can get it, or I don't have that book and I know I can get it, but you're going to have to wait, right? Because it's going to take, I don't know, a half hour to get it from Eros Station. Because again, the speed of light. If you want a physical book, it may take a week. So in terms of how we would construct this as a platform, this library would have to be able to answer my question. It would need to be available to me even if it can't guarantee the data that it's going to give me, right? So how does that work? If you think about eventually consistent databases, they may tell you I don't have that data, or they may give you a stale record. And if you demand a consistent read, it may say, okay, well, you can get that, but I'm going to have to make a call out to all of my nodes, and then I'm going to let you know, right? Which could take quite a while. So basically available, to contrast it with, in CAP theorem, availability, again, the way that I do that is I focus in on the responsibilities of the data. Now, Eventual consistency, the way I see that is it focuses on the process. So one of the things that they kind of cover a lot of is how the fog of war is, again, really impacted by the limitations of the speed of light, right? So if there's a space battle happening here, and because that's probably distracting too. This is a really cool scene, by the way, and I'm going to get distracted here. Something that you don't think about, but if you're going to wage war in space and expect that your ship is going to get hit by bullets, you probably should actually evacuate all of the atmosphere first so that you don't deal with decompression. So, so with eventual consistency, you know, it's almost as simple as it sounds. Basically, we just have to have faith that if we wait long enough, we will see the full picture, the consistent picture here, right? When we're talking about waging space battles, you know, if Earth is trying to communicate with the people in its area of operation, there's, you know, what, a 25-minute, 30-minute delay. Not only are they 30 minutes behind, but if they're getting information from other places, potentially they're getting information out of order, out of sequence, right? And if you think about how you would do this, what's interesting is this isn't modern, right? This isn't an issue that we deal with simply because we're in space. This is how wars have been waged since we invented war, right? Specifically, at the moment, you can't know exactly what's going on, right? You have kind of a picture that is delayed by a certain amount of time. But if you wait a day and you look back, you can actually put all of those things back together in order and actually have the full picture. Eventually, and eventual is relative to, you know, how this is constructed. You know, from a system perspective, you know, how frequently do you synchronize between your nodes? In space, what's the limitation of speed of light? Eventually, you will be able to look back at this thing and see the full picture. And then soft state, and I was thinking about using your ketchup bottle, Arnolfo, but you know, in thinking how to deal with this problem of soft state, it was pretty obvious that the metaphor I would use here is toilet paper. So, oh man, not even a giggle at the soft state toilet paper joke, whatever. Okay, no, but again, assuming that you know, you're in space and you don't have instant communications, there's going to be a station, right? Like, I don't know, maybe this is just something that I do, but I wondered about this, right? Like, which of the stations produces toilet paper and what's it made out of? Because I'm assuming it's not made out of trees. But you got to order that toilet paper, right? So what's the user experience there? Well, you can't, I mean, if the toilet paper is on the other side of the belt, you know, you can't afford to wait an hour to find out what, you know, whether or not they've got it and whether or not you're going to get it, right? The station that you're on has to keep a cache of it somewhere. So there's some warehouse somewhere, right, with crates full of toilet paper. That's its local cache. That's how it fulfills its local requests for that toilet paper. In addition, they're going to try to not run out, right? So they need to be able to read ahead or predict what its needs are and get those things to optimize that interaction between the remote station. And then finally, when you ask, hey, can I have toilet paper? It doesn't want you to actually wait until it sends a message out to some station somewhere else and gets the message back. So these are things that from an application design perspective, you really have to think through, right? Knowing that you can't be guaranteed consistency in distributed systems, or at least you can be, but it's really expensive, and you assume that you don't want to, then the application really has to think through, the application designers have to think through the consequences of that eventual consistency. So are there any questions about base? Okay. I'm either doing really good or this is the first talk in the morning. Okay, so the third question, the third act is what are messaging patterns and why do I need them? So in order to talk about this one, we're going to talk about hospitals. So I'm assuming everyone here has at least been to a hospital, if not had to deal with them. One of my favorite things about the medical industry is that they still use faxes. So the first messaging pattern that we're going to talk about are RPCs, or remote process calls, right? This is probably what most of us are familiar with, because this is when you have a consolidated system or a monolithic system. Most invocations of that system are remote process calls. They're built on top of a mature technology, usually HTTP over HTTP requests. From a hospital's perspective, if I have a doctor that needs records, right? Like if I go to my doctor and like, hey, I was in the hospital last week, I need to follow up, right? And the doctor's like, okay, yeah, I can do that, but I can't do that until I have the records, right? In most cases, and this is, I do find this ridiculous, but in most cases, you sign a paper form and they put it in a machine, and it sends an unencrypted message to some phone number that they hope is the right one on the other end. It sits in this machine until somebody comes along and picks it up, goes and finds the record, probably prints them out from their electronic medical record system, puts it back in the machine and sends it back to the doctor, and only when that doctor gets that thing back can they continue doing that original workflow that they started, right? Now, they may be doing other things in between, but the process that this RPC interrupts or sits in between is really blocked until they get these records back, right? So if you think about an HTTP request response, that's basically what this is. There are other forms of RPCs, but all of them are synchronous. They look synchronous, and they're usually built over asynchronous processes. It's not that remote process calls are bad. They are definitely overused. And if you like faxes, then continue to do it. So the second type is a stream. So NetSockets, WebSockets, if you guys have heard these in the technical perspective. But what a stream is, it's very similar to an RPC, but it maintains a connection, right? So rather than sending it and then hoping that somebody picks it up and returns it, in this case, the doctor picks up the phone, calls over to the hospital and says, hey, I need to talk to the attending who dealt with this person. I have a couple questions, right? And waits for the attending to get on the phone and has a back and forth. The difference is that in this case, that connection is maintained until the conversation is complete. Now, the downside of this is that it uses up more resources than an RPC, because with an RPC, it's only at the moment where it communicates, when it receives a request and when it sends a response, does it actually need that network socket. In the case of a stream, we create that network socket and we hold on to it until the conversation's done. Now, the benefit of it is that if we hold on to that stream, then the communications coming back to the originator, or going both ways actually, can be completely asynchronous, right? And in a distributed system, this is a really great way to manage a user experience, because without that, you don't have a lot of real options. The best option in an RPC world is to poll, to keep going back and saying, hey, do you have an update for me? Hey, do you have an update for me? Versus with a stream where you can be sure that until you're done with this conversation, you have a connection and you're able to maintain that. And a queue, if you've ever dealt with hospital waiting rooms, they're not fun, but generally first in, first out. And the reason that you have a queue is that it offloads the workflow, right? So rather than standing at the front desk until somebody can actually help you, what you do is you limit the interaction with the front desk to the point where they have enough information to send you to the chairs until somebody else can come and take you into a room and deal with you, and that's actually the next one, so I'll get to that. Generally, queues are the primary way to offload. In distributed systems, again, you don't want processes waiting on other processes, which wait on other processes, because those could end up in deadlocks. And it is much easier to create a deadlock in a distributed system than it is on a consolidated system. So queues are a very common way, and there are different types of queues. You know, the amount of robustness of the queue depends on what you're trying to do. But queues are a really great way to offload work so that they can be dealt with later. And if you've ever had to deal with you know, a really busy emergency room, they offload quickly. Okay, so asynchronous workflows. You know, having been through the queue, the next thing they do is they put you in a room, right? And you spend, what, an hour waiting there hoping that they didn't forget about you? Well, what this does is this allows them to start the workflow, right? Okay, well, we know that we need to take care of you. We're putting you in a room, and we know that eventually nurses will see you, doctors will see you, and you'll either get admitted or discharged, right? That workflow has begun, but it's not blocking anybody, right? And that's really the key with asynchronous workflows, is that they're designed to allow for the optimal execution of things without blocking the tasks, the systems, in this case, the staff, required to actually execute that workflow. Now, you can contrast asynchronous workflows with parallel workflows. Now, while parallel workflows are a type of asynchronous workflow, they're a very specific type of asynchronous workflow. So parallel workflows allow you to actually, whereas asynchronous workflows allow you to not block the people, in this case, or the systems that are fulfilling those tasks, parallel workflows actually takes advantage of the fact that you can have multiple systems or multiple components, in this case multiple staff members, perform tasks at the same time so that they can get done faster. Generally, in a hospital, this doesn't happen with doctors, but it may happen with nurses. You know, you may have, especially when you first end up in that room, you may have, you know, one nurse sticking you with a needle, another nurse preparing an IV, and another nurse asking you some questions. These are parallel workflows. How are we on time? 25 more minutes, okay. So, those are my messaging patterns. Were there any questions there? Okay. Okay, so for the next act of the story, we're talking about state machines and why they're important. So the concept of a state machine is not new. They've been talked about a lot. I can say that the innovation around state machines, the technology has made state machines much easier to work with recently. So to talk about state machines, we are going to talk about teen bully movies. And I do sort of a test, you know, whether or not you're a millennial by asking the question, Mean Girls or Heathers? And if you say, what's Heathers, then I know you're a millennial. And although Clueless, the bottom one there, is not a teen bully movie, I needed it for one of the metaphors here. So let's talk about call chain dependency problems. If you have a distributed system, if you have a distributed application, one issue that you deal with is trying to reason about what happens when a service calls a service, which calls a service, which calls a service, which calls a service, right? And it actually becomes a really, really difficult problem to deal with because you can't debug in a single step. You know, it's really difficult to debug a distributed system. You may have different languages. You'll definitely have different physical servers. The issues involved with trying to figure out what exactly happened in that call chain becomes really difficult. You usually end up having to build your own subsystem, which sort of weaves all those things together into a cohesive story, right? And then if you take a developer and point them at this problem, and you're like, hey, so somewhere along this line it's failing, right? You know, somewhere along the line we ended up with Peppermint Scooby Snack. And my son, who actually doesn't know who Benedict Cumberbatch is, was like, Peppermint Scooby Snack sounds good. Go figure out where that happened, right? How did we end up with Peppermint Scooby Snack? Well, the problem is that there's no way to audit in a way that's easy to reason about that entire chain of dependencies, right? So, you know, the metaphor I'm using here is, see, look at that, I got technical. You know, bullies often use rumors as a way to bully people, right? And, you know, I'm going to cover two ways to propagate rumors. One is to whisper into one ear and just sort of let it organically happen, right? Usually what ends up happening is by the time it gets to the victim, it is something completely different than what you said. It's usually worse. But you know, this is one way to sort of manage that message chain. Now, one problem with that is reentrance. So if you have seen this movie, Clueless, which is really the movie for my generation, Josh, who shares, I guess, ex-stepbrother, re-enters into her life. And you know, they immediately try to continue with the workflow that they had established before, which is this antagonistic relationship. But it quickly gets really, really confused because they're starting another workflow, which is romance, right? And we know that this is a feel-good movie, so we know how it's going to end. But from Cher's perspective, she's really confused, right? Because she's like, wait a second, I'm in one workflow, antagonism, but I'm also in another workflow, right? And so if you think about trying to design for this, having a component or a service or a method that has to understand that even though it's getting called, that it's getting called again and it's actually in a different workflow, can get really, really hard to reason about. It creates problems that are really hard to maintain over time. Even in a consolidated monolithic system, it's really hard to understand reentrance. But in a situation where the things that create that reentrant condition are out of your control, it gets even more difficult. So if we go back to this call chain, if you throw the red shirt girl, you know, somewhere else in this call chain, what does it mean, right? What does that mean for her Benadryl Cabbage Patch, right? Does she say Benadryl Cabbage Patch again, or does she mishear something else and say something different? So from just a pure reasoning about these problems, you know, call chain dependencies are difficult. Reentrance is even more difficult. I know this particular one is a stretch, but hopefully it resonates. So the solution is orchestration. Whenever possible, orchestration, which you may also hear under a number of different terms, Sagas, Actors, you know, there are a number of different ways to express this term. The general idea is that you will build a component whose specific job is to coordinate that. If we revisit the bully and the rumors, rather than sort of creating one entire rumor and passing it on to a person and then let that propagate through, what this bully is going to do now is actually break the rumor up into a number of different smaller rumors, which when they're all put together, they achieve the desired result, right? And then start whispering in many people's ears, and you know, the outcome should be that the subject or the victim of that bullying gets something much closer to what the bully had intended. And then the final one, and really the one that I struggled with the longest, is this concept of determinism and idempotency, right? First of all, I struggled with it because finding the right metaphor was difficult, but more because a lot of times there's confusion between the two. They're actually different, and I'm going to try to attempt to explain why. But they're similar, and they need each other very, very much, right? So I will have to admit to not having ever seen Mean Girls, and I'm sure all of the millennials will be like, oh my God, you didn't? But I didn't. I do know Tina Fey's in it as Sharon Norbury, and Tim Meadows, you know, my soul brother, is in it as Principal Duvall. Now the thing about these teen bully movies is that adults are one-dimensional and predictable, right? They usually don't change, And generally, once they've established what archetype that person is, you can expect the same result. Now, in terms of determinism, what that means is that when you deal with an adult, if you give them one input, like for example, hey, I'm being bullied, you will always get the same output. Okay, well, I'll call the bully into the office, right? So the decisions that are made are based entirely on the information that it receives and the things that it depends on, right? So in this case, you're telling Principal Duvall, hey, I'm being bullied. Principal Duvall pulls the bully into the office and lectures the bully, and that always happens in exactly the same way, right? That's determinism. Now, idempotency means that if I give something to a person, a service, whatever it is, right, that I know that if that thing is exactly the same, it won't produce a different result the second, third, fourth, fifth time, right? And so if you think about now, the Principal Duvall pulls the bully into the room and starts to lecture on, bad behavior, and the bully changes their behavior, but in this exact same way every single time, that's idempotency. And why this is important, why this is really, really important is, again, if we talk about the fact that we can't guarantee consistency, then the question inevitably comes up, well, how do I guarantee a transaction? Right? Like, if there is no consistency across the systems, how do I roll back a transaction if I get halfway through it? Right? How do I deal with these issues because we know that failures will happen? How do I deal with a partially completed thing? Well, there's two answers to that. One is you just do it again, right? So, if the orchestrator is deterministic, then all I need to do is give it the same data, and it will execute exactly the same way. And then if each of the things that it depends on are idempotent, then I won't produce a different side effect than what I expected the first time I called it, right? So that's ideal. And that's why these two things are really important, why they're different, and why they're also hard to describe. The other part of this is, if you can't do that, then you would call that deterministic service to delete those things, right? And then send them through again. If you can't guarantee idempotency, that's your only other option. I've had people say, well, can't you just build two-phase commits or distributed transactions into these systems? And the answer is yes, but generally the cost of doing that isn't worth the benefit, right? If we go back to what I talked about base, if you are exercising base in your design, then the need for a two-phase commit or a distributed transaction, so multi-phase commit, is mitigated by good design. So that ended Act 4? I said I was going to get you guys all woke up today, but I don't think that happened. Any Halo fans out there? Yeah. So you would recognize the Infinity, which was from Halo 4, I think. And what's interesting, it's funny because, going back to The Expanse, you guys don't know I'm a huge sci-fi fan. Going back to The Expanse, they kind of complain how in space, since you don't have to worry about aerodynamics, all spaceships are really, really ugly. They're just basically built like sideways office buildings. So to talk about infinite scale, and how are we doing on time, Arnolfo? Okay, good. We're going to talk about Blizzard games. So Blizzard makes a lot of games, and they're going to help me talk about infinite scale. So first of all, if somebody asks, well, what is infinite scale? The answer is imaginary. You're never going to need to scale to infinity. The idea is it's hyperbolic. The idea is that the scale to meet your needs will always be there if you design properly, right? So the first thing to design properly is horizontal scale. And so if you're not familiar with the Zerg rush, if you haven't been on the receiving end of one of these, what it means is that you'll be playing StarCraft, and you'll be putting together, you'll be building this nice base with really powerful units, and then suddenly a bunch of chumps, a bunch of Zerglings, right, just rush you and destroy everything in like 10 seconds. Well, the Zerg have horizontal scale figured out, right? So basically, the way that the Zerg looks at this is, what we really need is a bunch of really cheap units that I can create a lot of in a really short period of time, right? And I may support them with some really powerful things, but for the most part, their job is just to scale to whatever level I need, right? So I send out Zerglings, and if they're not enough, I just create more and I send them again, right? So horizontal scaling just really means designing such a way, again, using all of the techniques that I've talked about previously, so that you can add as many additional services as you can in order to meet the need. So on that topic, we got to talk about microservices. So, oh man, I played Hearthstone for a little while, but that is a time suck. So I had to stop. But if you're not familiar with Hearthstone, Hearthstone is a game that is composed of it's a card game, right? And you kind of have to collect these cards. And you have some general cards, but there are a lot of very, very specialized cards that do one thing and one thing alone. And the cards aren't really that useful in isolation, but if you create a balanced deck, then you have a lot of different cards that do different things, and they work together to actually be greater than the sum of their parts. And from a microservice perspective, it's not that different than that, right? What we're doing is we're building our deck. And you may start with a small number of cards, or less diversity in cards, but eventually, it's really about how you put together that deck in such a way that all of these little special things actually come together to become something that is better than if you had built it all in one place, right? So, I know that's an oversimplified representation of microservices, but really just think about it in that way, right? One of the discussions, and I have a hidden slide that I didn't show here. One of the things that I get into holy wars about is the idea of creating reusable packages that you can share between your services. Generally, what I would say is that if you're building microservices and you're trying to create reusable business logic, why isn't it a microservice, right? So, getting into that mindset, getting into the mindset of specialization is really important for microservices. And then we have containers. So here's another game that I've never played, but I hear it is pretty popular, right? Heroes of the Storm. Anybody? No, okay, well, I guess nobody else knows about Heroes of the Storm either. It's just one of the many MOBA games, like Dota. I'm using a lot of acronyms that I don't understand. But basically, the idea behind these games is that you create these builds, right? So these loadouts for each of these characters. So you start with the character, right? The character is your service. But in order to really use this character, you have to have an understanding of what upgrades and how you want to progress that character in a game. That is a definition of the environment required to have that character be successful. Well, what containers do is they take this idea of a microservice and they wrap it with the conditions required for that service to be successful in a server environment, right? So it's not just the code of the service, but it's the environment required for that service to be successful. The details on how that gets put together, the details on how these builds happen, is not really anything we need to concern ourselves with, right? So I guess in the perspective of Heroes of the Storm, it would be considered cheating. But if you could script out the creation of these builds, right? So like the first half of the game as you're playing and gaining levels, it just automatically picks the things. That would be what a container does, right? A container simply takes away the need to manually deal with these things so that you can go back to horizontal scaling. You can scale at whatever pace you need because you've taken the human out of the equation, right? So to get technical for a moment, what this means is the operating system, the ports, the protocols, and the tools required for that thing to run in a completely isolated environment. And then the last one is serverless. So if you remember Diablo 2, there's a necromancer character who could just really spam. I mean, like if you really wanted to hurt your friend's feelings, just create a bunch of skeletons, right? Because everybody's computers would start to grind to a halt. But again, the idea is that now we're talking about scale, but not actually needing to care about the environment at all, right? So, how can I create my code? So whereas with containers, we're talking about creating the environment where your code can succeed. With serverless, what we're talking about is creating code that can succeed in any environment, such that scaling them does not require additional things, additional scripting. You just simply create more of your code, right? It's not truly serverless. If you want to argue with me about how there's still a server there, I will simply say yes, and we call it serverless. Basically, you can continue to scale until you run out of money, or in this case, run out of mana. Is it mana? Mana? Yeah. All right, so that was it. I had no questions throughout. Do I still have no questions? Oh, man. Okay. Well, I don't know if you guys deserve the smile then, but thank you, everybody. I guess I still have some time, so if you want to come up and ask questions, we can do that. But I guess the presentation is over.